So in order to sum up the major and minor losses, we've got this equation: head loss total is equals to head loss major plus head loss minor. And if we take common v square root 2g from both terms, because for head loss major and head loss minor both have a common term called v square root 2g, so what we get is the friction factor either for laminar or for turbulent into length over diameter plus summation of all minor losses. Okay, so if I've got three components, then I'm going to sum up, let's say for union I'm going to sum up, then I'm going to sum up for a miter joint, and then I can sum up for let's say a contraction. Okay, so this is something which we can include for summation of all minor components, and the formula then simply goes that HL total is a summation of all the pipings for major and all the pipings for minor. Okay, where I represents basically a piping system with same diameter. Okay, so if I've got a system which has a different diameter, then I need to put additional again use a separate formula to, let's say this becomes J, and then Lj over Dj plus summation of all those minor components which are attached to their system. So this is basically valid for, let's say I've got a piping system where I've got same diameter but different joints. Okay, and then what happens is I've got a pump connected, and then the diameter reduces, to a different system. So I'm going to use this formula for this diameter system and this formula for this dia system. So that is why it is important that the I represents each pipe section with a constant diameter. Okay, so this is something which we need to take care of. So the objective of basically piping systems is basically to deliver fluids at same level or higher level. Okay, such as example a water tank, reservoirs, or perhaps to create a pressurized system such as hose, drill, or sprinkler system. So in these cases, in order to calculate the pressure at initial point or pressure at the final point, what we need is a modified Bernoulli or extended Bernoulli equation. Okay, what we do is basically we have the same equation, okay, only that we add the HL, which is the total loss due to the piping system. So previously what we learned was that Bernoulli was quite realistic, but then what we are doing is we are adding the real losses which are basically occurring in a piping system, and hence once we are going to solve the numericals, we are going to apply Bernoulli, but since the loss conditions are given, the friction factor is given, or perhaps the roughness of the pipe is given, then what we need to do is we need to consider the losses and then add them in our HL total. The reason is that we need to add more work is required at the end, and that is why we need to cater for HL, which is the total loss. As we know that when we have got a pipe, then we have got P1 and then we have got P2. So we know that the pressure at point 1 is higher than P2. The reason why is because of the losses. Okay, so that is why in order to equate this, what we need to do is we need to add losses in P2 so that we can equate P1 is equals to 8 P2, where P2 accommodates the losses, and that is why we are adding HL total in the P2 term. Last but not least, there are two principles when it comes to analysis of piping networks. No matter how complex they are based on two simple principles. Number one is conservation of mass throughout the system must be satisfied. This is done by requiring the total flow into a junction to be equal to the total flow out of the junction for all the junctions in the system. Also, the flow rate should remain constant in pipes connected, regardless of the changes in diameter. And number two is pressure drop. Basically, the head loss between two junctions must be same for all the parts between the two junctions. So for instance, I have got this point number 1, and I have got point number 2. Okay, so then the head loss will basically be a part between 1 and 2. So for pressure drop, if I've got point number 1 and then I've got point number 2, then the path between this junction, okay, whatever the path I'm going to follow, but it should have the same piping system, then the pressure drop between two junctions must be the same for all the path. Okay, so irrespective of the path, the pressure drop remain same. Whereas another thing is that the conservation of mass means that m dot is out in is equals to m dot out. So this ends chapter number 3 theory.